Yes.
Going to record this one too. So the length of a certain material like a metal is like a cylindrical cross section I'm going to take, and it has a cross sectional area of A, and the free electron density, which is called the free electron density, I'm going to take it like N. N equals what? So technically number of electrons, free electrons in a unit volume. Unit volume means 1 cubic meter, right? This is what the free electron density or the delocalized electron density. And so the motion is not actually moving like this straight away. Why? Because the electron may have to collide against this one and collide back and forth. Actually, this one will have to collide millions of billions of times with the other nuclei of the material to reach to the other end, right? Even though it has a really high speed, it can't travel like this way. The velocity factor is a really smaller one. Can you understand that?
Yeah.
We used to know that car drifting. Car drifting means the wheels are rotating really faster, but the car is just sliding down, just sliding like this, slow. Why? Even though the wheels are really spinning faster, car doesn't move that fast. That's the same thing happens. So the electrons are actually moving really fast, but the real velocity towards the positive end from negative end is really slow. So this velocity is supposed to be known as what? We used to call this one as Vd or drift velocity, right? That's known as drift velocity. How to find it out? One thing is certain: the charge current is what? Q over T. This is equation number 1. So by the way, what is the charge? Charge is nothing other than of an object, number of electrons times the charge of an electron. Can you understand? But here I'm going to get one as capital N because to avoid any confusion, because this one is like already mentioned, like capital N, simple N, number of electrons times of mass electrons. So, equation number 2. Now I can happily include this one there, 2 into 1, and this equation becomes N E over T. Right. So, how to find out this N? According to the free electron density of N and the cross-sectional area A and L. So I just firstly mentioned certain equation like here N equals to N over V. Isn't that? N equals to density equals to capital N over V. So when you cross multiply, N equals what? Simple N times V. Isn't that? V is the volume. This is equation number 3.
So what's simple N again?
Simple N is the charge density. So capital N is
yeah,
the
okay,
number of electrons, right? Or you may use it like N dash whatever. Got the point?
Yes, sir, got it.
Okay. So what is this volume? What is this volume? Volume is what? Cross-sectional area into length. Isn't that? Equation number 5. Now I can include equation number 5 into equation number 4. Then my equation becomes what? Capital N equals to N A L. Okay. This one is number 6. Now what you have to do? This equation is equation number 3. I can include equation number 6 into equation number 3. Equation number 6 into equation number 3. Now this becomes I equals what? N A L and E over T. Right? This looks really ugly for me. What can I do is I can get N A and I may get L over T here. What is this fact? L over T, length over time.
Velocity.
Velocity. So finally my equation becomes I equals to NA VE. This is how it should get derived. Understand the derivation?
Yeah.
Okay, very simple. It's a really simple derivation. If you derive it like in this manner, you may easily understand it. So I minimize it for one more time. Okay, copy this to your book now. Final equation you already know. Copy. Yeah, try this question. Question number 7. So yeah, I'll give maximum about 6 minutes to do this one. Okay, guys. Finished. Do you finish this one, or do you need
So
more
can
time?
we like 3 more minutes?
3 more minutes. Okay.
Yeah.
So look at here. An integrated circuit, that means IC, uses strips of gold as connectors and strips of silicon as resistors. Right. Strip of gold of cross-sectional area 3 10 to the power minus 6 meters, and the current is like 8 milliampere. Charge density is like 6 into 10 to the power minus 28 cubic meter. So that the velocity for gold is approximately this much. Right? How I equals to NA VE. So the velocity is the one you just need to get. Velocity equals to I over N A. So what is my I value here? It's like 8 milliampere 10 to the power minus 3, and A is what? It's like area as we given the area. Yeah, 3 to 10 to the power minus 6, and sorry, wrong application. The number of electrons is given like that's 6 or 8. 6 10 to the power minus 28 multiplied by area is 3 into 10 to the power minus 6, and E, charge of an electron. Charge of an electron you have to remember, because in the exam you get the data sheet. So it's like here. So apply these values in your calculator and you may get a value of this one. So you get any answer close to this one?
So you get 2.777, so 2.78 into 10 to the power minus 7.
Minus 7. So that means this is approximately closer to the value of what? 3 into 10 to the power minus 7 ms minus 1. An approximate value V for the sample of silicon with the same dimension, that means length and area going to be the same. It's going to be what? 0.2 ms minus 1. Compare this value with 1 volt and for the difference in values. What about? So you know one thing, what? The same current, I equals to NAVE. So the same current, nothing changes. This one is same. So this one is same, area is same. So what about the speed? The speed has raised by many million times. So what is the thing then changing here? So as to maintain the same but current here, the number of electrons has to drop dramatically. Understand?
Yeah.
So the silicon contains what? Contains
Low
lesser,
charge density.
yeah, lesser or lower charge density than what? It's
And gold.
Right. State and explain what happens to the resistance of a sample of silicon as temperature increase. You have to compare this value with the, what is it called? Wait. The comparison of the values changes here. There was a chart here. Silicon. See what happens in silicon. There are all the other resistors. The value actually decrease. See, copper, aluminium, all decrease. But in the semiconductor materials like silicon and germanium, what happens as the temperature increase?
Conductivity increases.
Yeah, the free electron density keep increasing. All right. Silicon is a semiconductor material. In semiconductor materials, what happens? So the number of free electron density or the delocalized electron density increases with temperature. So as the temperature increases, what happens? The conductivity of the silicon chip increases while reducing what? The resistivity. Okay, so the resistance is reducing as the temperature increases. Understand?
Yes.
Guys, understood this one or not?
Yes, sir.
Okay,
Yeah,
good.
got it, sir.